Good morning, everyone. Welcome to today's webinar for electrical motors, troubleshooting and understanding them. We are here with our technical expert today, Bob Kluke, and my name is Ryan Smith, another fellow instructor and product manager with TPC Training. So we're here to deliver to you a nice 1-hour session of some really good technical little tidbit of training on motors. Lots to learn here about how they work, and Bob's going to walk us through. Bob is our resident expert in electrical training here at TPC Training. He's been with us for over 10 years now, and he's been in the industry for many, many more. He holds an associate's degree in electrical power and a bachelor's degree in education, and he's also a non-restricted electrical contractor. So he's seen and done it all in this industry, and we look forward to learning from him. So without further ado, take it away, Bob.
Thank you so much, Ryan, and welcome, everyone. I'm going to start this with this definition of qualified person, and I want to give you an idea why I want to start this way, is because I believe that no matter what we are trying to troubleshoot, we should really understand that equipment very well before we just start going in there and putting a meter on things. So we really should be qualified to work with motors before we actually go and troubleshoot them. So a qualified person, of course, is somebody who has some skills. They can show me that they can do those things. They've got some great knowledge about whatever the topic is that we're working on, how the equipment was built, how that equipment operates, how that equipment was installed. And then, of course, they have to be safe around that equipment. So they have to be able to identify any hazards. And of course, in the electrical trade, we usually talk about shock and arc flash and arc blast, but sometimes with motors, we've got to look at the rotation and know that that rotating part could cause some damage. Also, we have to look at maybe the weight of the motor and how heavy it is. And then we have to be able to mitigate any of those hazards that we might come up with. So all of our courses, whether they're a webinar like this or it's an open seminar or an on-site, we always try to stress that you're gonna be a better qualified person after you've taken any of our courses.
And I'll take this opportunity, Bob,
Sure.
to give people a quick bit of instructions on if you have questions as Bob talks throughout this next hour. There is a way to ask questions to us, and we'll be able to answer them toward the end of the session. So if any of you go to the bottom of your screen here, you see on Motor Rotation Basics, you're going to see a chat button. You can go ahead and click that chat button and type in your message there to all panelists. Make sure you're not clicking all attendees, or it'll go to all over 100 people on this webinar. But you want to go to all panelists, type in your question, and I will collect them on our behalf as our host here, and I'll be able to ask those questions for you guys at the end of the session. So feel free to ask, and we'll have a great Q&A at the end of the session. Also, I wanted to let everyone know, if you're curious on whether these slides will be available to you after the webinar is over, the answer is absolutely yes. So we'll be sending a PDF version of these slides to you after this webinar is concluded within 2 business days of this webinar. So look forward to that, and thank you so much. Take it away again, Bob. Thanks.
Okay, no problem. And thank you, Ryan, for that, so that they know how to submit questions. The information itself will probably go for about 45 minutes, and then we'll have roughly 15 minutes for any questions. So we'll answer those questions at the end of the presentation, so no problem about that. Okay, it starts with magnetism, and I like to tell my students that electricity and magnetism are married together. When you have one, you can have the other. And so a lot of our discussion today will be about alternating current motors. And so what I want to remind people is that with our, let's say, sine wave that we have, and I'm going to attempt to draw a sine wave, so there it is right there, that magnetic field will also get larger when we get to the top of the sine wave, and then it'll decrease some. So the magnetic field is always on the move, so it's moving all the time. And all our motor is basically a rotating transformer. So if that sine wave is getting larger and smaller, then our magnetic field is getting larger and smaller, and we are inducing a current into the rotor section, the part that actually turns, and that makes things go so easy. I mean, it's really nice. So, and when I change around here a little bit, I get back to where I want. So magnetism. So now we can see some different types of motors that we might have to deal with. And DC motors are very strong motors. They produce a lot of torque, great for speed control. But most of our discussion today will deal with the two bottom two, some single-phase motors and three-phase motors. If we go back in time to the late 1800s, the great scientist Nikola Tesla did develop the three-phase induction motor. And in fact, he first called it a rotating transformer. So he could see that magnetic field rotating 360 degrees, and then it would bring the rotor with it. And so very basic. Really, we only have one moving part in the motor, which is the rotor. So it's kind of a basic construction type of device, but does tremendous amount of work for us. In fact, sparked the Industrial Revolution. And today it is still, in 2019, one of the top 10 greatest inventions in the history of the world. So we will be looking at something that is very important in our world. So if we go back in time, the Greeks discovered that like magnetic forces will repel, unlike will attract. Well, that's what gives us our rotation, is that we established two magnetic fields, one in the stationary part, which is going to be our stator windings, and the other is in the rotating part, which is going to be our rotor. And these two magnetic fields, of course, are going to be opposite in polarity, so they're going to attract each other, but it's also rotating 360 degrees, so it's going to bring that rotor right with it and cause that spinning sensation that we have. How we determine the current and type of motor would be, of course, how the manufacturer built it and what our specifications were. A lot of DC motors today we might see on forklifts, maybe in the railroad industry, but with the advent of variable frequency drives, we certainly are very prevalent with that AC motor. So here we can see the two basic parts. So here we have our housing on the outside, but right inside that housing you can see our stator windings. So those are stationary, and they help us with the magnetic field. When we energize these windings, the magnetic field will tend to rotate all around. And while it's doing that, we have to remember that it's getting larger and smaller, so it's moving, and it will induce another magnetic field in this rotor. And then as the magnetic field rotates around this stationary part, the magnetic field will bring this rotor right with it. And depending on how many poles that we have for that motor, whatever the manufacturer built for us, if it's a two-pole motor, the rotor will turn at 3,600 RPM. If it's a four-pole motor, it's going to turn close to 1,800 RPM, maybe a little bit less in each case because of something that we call slip, where the rotor really never catches up to the magnetic field in an induction motor. But the basic concept I'd like to have you understand right here is we do have a magnetic field that is rotating 360 degrees. The speed of that magnetic field is dependent upon how many poles that the manufacturer gave us in the motor. And the most common number of poles would be 4 for an induction motor. Here we can actually see a cutaway version of the motor. And what I really want to try to impress upon you is right here is that stator winding where you can see my cursor moving. And then you can see the rotor. There might be a 16th of an inch gap there, but they're very close to each other so that we can maximize the power of that magnetic field. And how well do we maximize that power? Well, if this motor even was a 1 horsepower motor, let's say, and maybe on a swimming pool, a pump for a swimming pool, the only force that's turning this rotor is the force of magnetism. And even on a 1 horsepower motor, which is a fairly small motor, we can't even put our hand on that shaft and try to stop it. That's how powerful that magnetic field is. A few more parts that we are going to see here. And we can see that the stator and the rotor very easily. But then we have a fan over here on the left-hand side, way near the end. And that fan is going to help cool the windings in the motor. So sometimes we have to be a little careful about that, especially if we put our motor on a VFD, because if the fan turns slower, then we don't get as much air across our windings, and our cooling effect is going to be impacted, and that's not a good day. We have on top an eye bolt, and then of course we have the frame, and you can see that the frame has what looks like some fins on it, and that's like a heat sink that is going to help us dissipate the heat that this motor would generate as it's spinning. Of course, we always should remember this, that whenever we have current flowing, that does produce heat, and we want to make sure that we can dissipate that heat and have our motor last a very long time. We have we have a grease inlet where we could grease the motor because these are not sealed bearings. And we have a place that we could drain the grease out, and a few gaskets. Here's our conduit box where we would terminate our conductors and supply power to that motor. So basically the basic parts of a motor, but remember what makes that rotor turn is that magnetic field that spins all the way around. So that's what we really want you to remember here. So we're going to look a little bit at motor terminology and some standard definitions. And all of this came out of a standard. And of course, we have lots of standards. ANSI comes up with standards. The NFPA comes up with standards, IEEE. Well, this standard came from NEMA, the National Electrical Manufacturers Association. And it is a standard and a guide to select, install, and use electric motors and generators. So it's the MG2 standard. It was revised in 2014. It can be purchased from NEMA. It has a lot of information on it, but all of the terminology that I'm about to pass on to you, you will see came from this standard. And I just wanted to let you know that it is out there. So we're looking at a nameplate here, and we can see that a 50 horsepower motor right up at the very top. The first thing goes through my mind when we hear 50 horsepower motor is that motor is a very heavy motor. So we're looking at 800-900 pounds at a minimum. Notice that the revolutions per minute, the RPM, 1765. So immediately I know this is a full pole motor because the magnetic field is spinning at 1800 RPM, but the rotor itself is only turning at 1765, and the difference is what we call slip. And an induction motor really never quite catches up to that magnetic field. And when we have that phenomenon, that gives us our rotation. It allows that north and south to attract and bring the rotor right with it. The frame has an interesting number in front of it. So the letter behind it, the T, that signifies that it's just a standard shape frame. So sometimes you might see a U behind that number. It'd be a U-shaped frame. In this case, the T signifies standard. But the number gives us some good information. If we take the first two numbers, which are 32, and we divide those by 4, that would give us 8. So if I come back to this picture right here, from the bottom of our frame to the midpoint of that shaft, it's going to be 8 inches high. So when you take those first two numbers and divide them by 4, it will tell you the midpoint of our shaft. If you take that last number, which is 6, and if you divide that by 2, then you get 3, and that means the shaft is sticking 3 inches out of the housing of that motor. So the first two numbers we divide by 4, that gives us the height. The last number we divide by 2, and that tells us how far out the shaft is coming out of the frame of that motor. It's a dual voltage motor. So over here on the left-hand side where we show you the different connection points, what we really want to give you an idea about is when you have a dual voltage motor like this, basically when we connect it to the higher voltage, we're taking each winding and connecting those in series with each other. And if we go, because in a series circuit, we know that the voltage adds up to the total. So if I took, for instance, the A winding, and I cut that A winding right in half, but I connected each half in series, then I would have 230 on one half, 230 on the other half. It would add up to my 460. If I wanted to go with the low voltage, then I would connect those windings in parallel. And when I did that in a parallel circuit, the voltage stays the same. So I would still have 230 on one winding and 230 on the other. But because of the different configuration, either series or parallel, that allows me to have the ability to connect it either into a low voltage or a higher voltage. It is a three-phase motor, 60 hertz, so made for the USA. Then we can see the FLA, 122 for the lower voltage and 61 amps for the higher voltage. And I want you to remember that a little bit because I'm going to come back to that FLA some. It is a continuous duty motor, so it can run 365 days a year, 24 hours a day, and all motors are continuous duty, by the way. The next little section tells us that it can be used on 208 volts, and if it does, our current, of course, our voltage goes down, so our current is going to go up to about 140 amps, and we might not have the same horsepower. So it may not meet all of the National Electrical Manufacturers Association performance limits if we do go to that lower voltage, but we should understand that definitely it is going to be real close, extremely close. The next thing we see is insulation, and it says F. So the insulation that they're talking about here is the insulation that's actually on our stator windings. So those stationary windings that allow me to have that rotating magnetic field, we have to put insulation on those, and the insulation can either be A, B, F, or H. In this instance, it's F, which is the third best insulation we have, which would give me up near 160 degrees Celsius. So the insulation is important. F is really good. If I had an inverter-rated motor, I would probably see H, which is the highest insulation we could have. The next thing that I see is the service factor, and it says 1.15. Well, the service factor means that if I ever go over this FLA, the full load amps, I can actually go above that number by 115%, and my motor's not going to be damaged. So it's a direct reflection of how much I can overload this motor and then still not worry about damaging the motor. The next thing we see is a NEMA code G, and I would have to get into Article 430 of the National Electrical Code. There's a table in that article about locked rotor, and what that table tells us for the letter G, there would be a number in there, and that number, let's say, could be the number 5. Well, if that shaft or that rotor froze and would not turn, it's going to give us an idea how much current would flow. So you take 5 times, let's say, the lower amps, because we're on the higher voltage, so 5 times 61, that motor is going to draw about 300 amps, either on startup when it's not turning at all, or if the rotor freezes up on us. It is a NEMA Design B motor. So the NEMA design gives us great information about the torque characteristics of the motor. And a Design B motor has normal starting torque, normal running torque. So that's good. If it happened to be a Design D motor, then we would have high starting torque and high running torque like a winch. But this is your basic three-phase induction motor we're looking at. So, should be fairly easily to understand normal starting torque, normal running torque. They don't want us to install it in an ambient temperature above 40 degrees Celsius. And then it says temperature rise, 70 degrees Celsius. So what that temperature rise means is that's the allowable rise of the temperature of the windings inside over the ambient. So the stator windings are definitely going to produce heat because I have current flowing through them, and when that heat is produced, they don't ever want us to go above 70 degrees Celsius compared to the ambient. And so understand that that's how hot it can get before the insulation is going to be damaged. Gives me a little bit information about efficiency. And then up here in the top right, I see TEFC. So that would be totally enclosed fan cooled. And so now we're getting some information about our motor, so that's good. We're going to be troubleshooting that in a minute here, but first I want to look at these diagrams. You can see low voltage. We brought out 12 leads on this motor. So we can do a lot when we bring out 12 leads, and basically what does that mean? We have 3 windings inside, so each winding we divide it up into fourths. So each winding is really, instead of one large winding, it's 4 little windings. And by bringing those 12 leads out, we can have many different configurations. What we used here was for low voltage, so that would be in parallel, or high voltage, and that would be in series. But by bringing 12 leads out, we could actually start that motor in a delta configuration and then transfer over to a Y as we got our speed up. So I did say that I wanted you to really think about this FLA, the 61 amps at 460 volts. Remember, it is a 50 horsepower motor, because the next slide that I have does not say FLA at the top. It says FLC. So the FLA that we saw on the motor, the 61 amps, that's full load amps, comes right off the motor nameplate. This is full load current, and it comes out of the National Electrical Code. This number will always be higher than the FLA that we see on the nameplate. So if we come to our 50 horsepower motor and we come over to 460 volts, we can see the number is 65. It's close. Over here we had 61, but this number over here will always be higher. And we have to use this number, this 65 number, to choose our wire size of the motor, to choose, let's say, our disconnect, to choose our overcurrent protection, whether it be an inverse time breaker or time delay fuses. We have to use the FLC. What we would use the FLA for would be to choose our overload protection. So a little bit of test equipment that we're going to need to be able to troubleshoot this motor. And some of this might look a little bit sophisticated, but I do want to mention that this, the yellow meter from Fluke, is a T5 600. So that is basically your basic multimeter. It'll test volts for you, it'll test amperage, and it'll test resistance. So that's a great meter. Then the one in the middle, and you can see from Amprobe that has a M and then an ohm symbol behind it. That's a mega. So and that mega is going to be used to test the insulation. The regular multimeter we're going to use to test the windings, and we could also, if we were troubleshooting and we had to trace voltage with the multimeter, we definitely could do that. Just to the left of the multimeter, we see a little pen tester, and I can tell you that the pen tester also works off the theory of that changing magnetic field. So it works off induction, just like the motor works off it. So we got to be careful with the pen tester, because if there is just stored energy, let's say, for instance, a capacitor, then that pen tester might not pick it up. So we got to be careful with the pen tester. It's good for a quick check, but much better to put the multimeter on that circuit. So I wanted to give you a little diagram here. We're going to start with single phase, and it's a capacitor start motor. Normally, right here, the CS, the centrifugal switch, that would normally be closed on startup. And so what would happen is when we apply power to L1, L2, my centrifugal switch would be closed, and that would allow power to get to my start winding, the winding way over to the right. We'd be able to have power there, no problem. And we would be using the capacitor for a couple things. One, the capacitor is going to charge up to the peak of the sine wave. So if I'm using 120 volts for this single-phase motor, the capacitor is going to charge up to 170. That's going to help me start this motor a little bit more efficiently. Plus, by putting the capacitor in the circuit, it gives me a little bit of a phase shift, and that phase shift helps me with rotation on a single-phase motor. But once we build up to 75% of our RPM of this motor, this centrifugal switch will open up, take the start winding out, and we'd be just running on the run winding. So a lot of single-phase motors will have that capacitor start on them. So what can we do? We understand that, let's say we just wanted to check our motor initially right out of the box. A lot of times when that motor comes out of the box, there's a lot of things I'm going to check. One, I'm going to make sure it'll turn, because in shipping, sometimes the housing for the fan might get bent in and the fan doesn't turn, then the shaft won't turn, or a variety of reasons that it might not turn. So one, make sure it turns very easily. Two, make sure there's no play in the rotor. We don't want any vertical or horizontal play. And then one of the last things I'm going to do is I'm just going to put an ohm meter on L1 and L2. This is before I even install the motor, because what will happen when I do that is it will give me a resistance of what the motor is when it's just sitting there. So we definitely would be reading straight through the one run winding. Probably couldn't read through the capacitor, but it would tell us if the run winding is good or bad. And then one of the last things that I want to mention on this particular diagram is that if we were ever going to reverse a single-phase motor, we have to actually bring out T8 and T5. And so a drum switch works very well with that. You can really reverse that really well, bring those leads out. You can have forward, reverse, or you could even have off in the middle position. So on a single-phase motor, know that T8 and T5, that's what we have to actually reverse. Now, we're still looking at a single-phase motor, but this motor is dual voltage, just like the one in the nameplate we saw a little bit. And basically, we have our starting winding, which is way over here to the right again, help us start the motor. No capacitor in this motor, didn't need one, but we have our centrifugal switch there. And then what we have over here to the left, where we see T1, T2, T3, T4, that is our main winding. We divided it up in half, just like I mentioned before. Why did we do that? Because if I connect these windings in series, I can go with the higher voltage. If I connect these two windings in parallel, I go with the lower voltage. So I wanted to make sure that you had a good handle on that. Next, we're going to come to three-phase motors. And three-phase motors can be wound in a couple different ways. One, it could be wound what you see on the left, which is a delta configuration. And in that configuration, we would make it look like a triangle, just like it does right here. But that delta gives us more torque on startup. So if I had a very large motor and it was very difficult to start that motor because of the load we connected to it, then I would want that motor wound in a delta configuration. The Y configuration to the right, that gives us better speed control. So depending on what we need in our facility, do we need something with a lot of torque? Is it a slow-moving crane or whatever? Or do we need something that has great speed control? That would make a determination of the motor that we want to purchase. And the cutoff usually for this is right near 25 horsepower. Above 25 horsepower, you're going to see a lot of delta wound motors. Below 25 horsepower, you're going to see a lot of Y wound motors. So now we come to a little pictorial of that three-phase motor. And we can see that we have phase A, phase B, phase C, each one of these a solid winding, right? And what happens with this is that we can connect this either in a Y or a delta configuration. This is going to be a Y configuration for us, and we're going to bring out first T1, then T2, and then T3. So I mentioned earlier that we need that multimeter to go ahead and identify if our windings are good or not. So basically what I would do with just a regular ohm meter, I would put one lead on T1, one lead on T2, and that is going to force the current straight through winding A, also straight through winding B, and then it would come back out to my ohm meter. So if I put that meter right between T1 and T2, I can identify immediately if A and B windings are good. What should I get when I do that for a reading? Well, I should get on a regular three-phase induction motor, a number between 10 and 30 is real good. Now, I have seen on some high-efficiency motors that reading be up near 150 ohms. It all depends how the motor was wound and how the manufacturer developed their windings. So the two numbers that we don't want to see, and one of them on a digital meter would be OL, which signifies open line, and that would mean that one of these windings was open, and of course when a circuit is open, we have no current flowing, and if no current can flow, then we're not going to be able to turn that motor. So OL is not a great thing to see. The other number that's not a great thing to see would be 0 ohms. And so 0 ohms would mean that somewhere phase A and phase B are touching, and that would be a short circuit. And so, of course, OL is bad because we're not going to have any current flowing at all. A short circuit is bad because we're having too much current flow. And in a short circuit, of course, all the current that the transformer can deliver, wherever this motor is going to be installed, that's how much current would flow. And many times, and a lot of people don't realize this, but that short circuit current can get up to 20, 30, 40,000 amps, depending on the size of the wire and the size of my transformer. And that's what causes an arc flash explosion. So we definitely want to make a determination if those windings are shorted with each other, because if we don't, we are going to definitely have the capability of causing some type of injury to ourselves or damage to more equipment that might be around this motor. So we would do that between T1 and T2. We would get a reading. Let's say the reading is 18 ohms. Then we would go to T1 and T3, and we would want to see that exact same number, 18 ohms. And then we would go between T1 and T3. So we would be checking all three of these windings. We're checking two at one time, but by going between T1 and T2, and then T2 and T3, and then T1 and T3, it would tell me if all my windings were good or not. And if I got 18 ohms on T1 and T2, I better see 18 ohms on T2 and T3, and 18 ohms on T1 and T3. So all we're doing with the ohm meter is just checking to see if our windings are good or not. And if we do see a bad reading, we know that OL, the motor won't start. We know 0 ohms, there could be an explosion. So that's one of the checks that we can see. Now, what could cause the windings to maybe be shorted together? It could be maybe that somebody actually put too much grease in that motor, and that grease has to go somewhere, and it can get into our windings and cause a short circuit. So whenever you lubricate a motor, you always want to go by the manufacturer's instructions. We have a lot of motors today that have sealed bearings, so we don't have to worry a whole lot about lubricating those. But still, a lot of motors do have regular bearings that we have to lubricate. You have to make sure that you have the right grease. You can't just put in any old grease you want, and then you have to make sure that you know how much grease to put in. a half a pump, 1 pump. You start going over 1 pump, you want to be really reading that manual that came with the manufacturer. So then back here, a few slides when I had my meters up there, I was showing you the T5600 that sort of had a fork on it, which is where I could measure current. So sometimes we call that an amp clamp. That one had that fork. I just stick the wire in between those two protrusions on the meter. But a lot of it have an amp clamp, and that's going to give us some great information that we have power on the motor's turning. Maybe the motor's being fed from a disconnect switch or a motor control center. But what I can do on the load side of that disconnect or on the load side of that motor starter in an MCC, I can clamp around each one of those phases. And it's going to tell me how much current that motor is drawing. This is a great check, because if I'm overloaded a little bit, I might not have any physical indication to me. You know, it doesn't seem that the motor's running any hotter than it should be. Nothing has tripped off. And so by putting my amp clamp around each phase, first phase A, then phase B, then phase C, if we take the motor that we had the nameplate on and we're at the higher voltage, when I go around phase A, I should see 61 amps. And then when I go around phase B, I better see 61 amps again, and then 61 amps around phase C. And that tells me a lot. That tells me that I haven't overloaded the motor, so the motor's working within its operating range. It tells me that I have no circulating currents going between the windings, which could cause the motor to overheat. And it's a great check. So that's one thing that we can do and look for, and it works out real well. The meters that are nice to use are these true RMS meters. And so a true RMS meter really gives me a good look at the sine wave. If I do have a meter that does have an oscilloscope on it and I can actually see the sine wave, that's great. But I can tell you that if your motor is connected to a VFD, if you do have a meter that has an oscilloscope on it, you can determine if that sine wave has been distorted or not. And that's a very valuable tool. So the better meter we have, the better we can do diagnosing our situation. So now I'm going to talk a little bit about the other check that we have to do on motors, and that is to check the quality of the insulation on those stator windings. So I've already talked about just checking if the winding is intact or checking if the winding is shorted. That's a very important step that we have to take. And also this step, which checks if the insulation is good or not. And so this is called megging out the windings. If the insulation is not good, then we're going to have what we call a ground fault, and that would be a phase conductor coming in contact with our equipment grounding path, a very low resistance, a very high current is going to flow there, just like it does in a short circuit situation. So if we tried to start the motor under a ground fault situation, then certainly we would have something trip off or something explode or somebody get hurt. So we always want to make a good determination what the quality of the insulation on the windings are. And the other thing that allows us to do is that really allows us to make a good prediction of when that motor might fail. So it's just a great tool. It's something that we should routinely do. Many people do this semi-annually. Some people will do it annually, but it is going to test for a ground fault, which means, did my insulation deteriorate to the point where one of those bare wires is now hitting the frame of the motor? So that's what we're looking for, to see the quality of the insulation. We can do this on motors or generators, anything that has insulation on it, basically. So, but we're going to be using it, of course, on motors. This slide tells us to make sure that we've disconnected the motor, that we don't have it connected to a drive when we do this test, because the megger will build up a very high voltage, and it could damage any electronics that that might be associated with that circuit. So here's what we do. This is an old style megger. In today's world, we're probably going to have an electronic megger where we just have to push a button. This one is the crank style megger that I grew up with, but you know, now I have meggers that are just made a little bit better. But we're going to take the red lead, the meg ohm lead, and it's going to go to T1. We're going to take the earth lead or the common lead, and it's going to go to the frame of the motor. When we put this on the frame of the motor, we'd like to put it in a place where there's no paint. We want a real good connection to the frame of that motor. And in this case, we would start turning the crank and see what it gave us for a reading. But with a digital megger, you just have to press a button, and then the meter will cycle through and give us a number. And the National Electrical Testing Association recommends that we have at least 5 megohms. If you ever get down near 1 megohm, then that motor's not going to start. It's hopefully going to trip a breaker or open up a fuse, so we don't cause any damage to personnel or equipment. But we're really looking at 5 megohms as the minimum number to determine here. But the higher that number, the better my insulation is. So the best number we could have, again, would be OL, or open circuit, which would just mean we can't force any electrons through the insulation on that wire. That means we have some great insulation. So once I did T1, I would move my red lead to T2. Then I would move my red lead to T3, check all 3 windings, and make sure that that insulation is above 5 megohms. And hopefully it's up near open line, which is the best that we could possibly have. So here's some causes of motor failure. And we can see right off the bat that we overloaded the motor, and it created a lot of heat when we overloaded the motor because it was drawing more current, and it caused my insulation to fail. And that insulation, of course, would be on the stator windings. And when it failed, you know, we would develop a short circuit. So the megger could help us determine of when this could happen. If we are vigilant and doing our meg test semi-annually or annually, and that number starts to get now down near 5, we could tell the boss, hey, be careful, because, you know, we're getting ready to have a motor go on us. Contaminants are also an issue. So I know in a lot of food processing facilities, we have to hose down and a lot of water everywhere, or our grain facilities, there's dust or whatever. And it's important to try to keep our motors clean. And so I would love to have a vacuum around. We vacuum things out. If we do lose a phase, that's going to cause circulating currents in my motor. That's going to cause extra heat, cause the motor to fail. Same with the bearing. If the motor is turning harder than it should be, cause extra heat for us, motor will fail. Excuse me. Or just natural aging or misalignment, rotor failure. All these things we want to try to take care of in our PMs, and we can do that with our meters, megging out with our eyes, looking at the contaminants, of course, with our ears, listening to the bearings. So all those things would definitely come into play. So heat is our enemy, of course, in the electrical trade, and you know, we can take a thermal image of our motor. What a great diagnostic tool that is. And we take that thermal image, and it could tell us immediately if that motor is running too hot or not. And the camera just does not lie. It's always going to give us a true picture of what we see. So the overheating of motors, we can take care of that a little bit with thermal imaging, with our amp meter, sometimes even with our hands. Then you can see a poor power condition. So if we did have some power quality issues in the facility, that could cause some overheating. Those power quality issues could be low voltage, it could be harmonics, it could be transients. If the service factor, if we exceeded the parameter of the service factor, frequent start and stops, environmental, all would cause overheating of that motor. So we got to keep our eyes and ears open to see what is going on with our motor. But this is a slide that I really like, because right at the top it tells me something that I always love to do, and that is look for the obvious. So as I'm walking through the facility, I'm going to be all eyes, all ears. I might even put my hand on some of these motors just to get an idea, but my eyes and my ears and my hands will give me a lot of information. So a lot of this will be review for us for this, that, we're just looking for overheating, whatever, maybe with a thermal imaging camera or whatever, some coupling problems, maybe it's a belt-driven type of a circuit. The ambient temperature got too high. The mechanical checks I mentioned before, we want to make sure the shaft will turn and no vertical or horizontal movement. That tells me something about the bearings. And then the electrical checks, remember the clamp-on ammeter when the motor is running is a great diagnostic tool. And when the motor is not running, we definitely can check the windings with a regular ohm meter, and we can check the insulation with a megger. The overloads are something that we might have to take a look at if our motor is giving us a little bit of problem with starting or tripping off all the time. And they can be basically three different types. They can either be a thermal type of a sensor, where it is going to determine how much heat is traveling in the circuit. So those are two different types. Solder pot, where we have a little chamber that is filled with solder that will melt if it gets too hot. And when it melts, it's going to trip a switch that will shut off our coil on our motor starter. Or they could be bimetallic, and too much heat flows through, and that could open up those two pieces of metal and prevent the motor from overheating. Or we could have some magnetic sensors, or in the case of a variable frequency drive, they could all be solid state sensors. So electronics could help us with that motor. But this is some things that we have to check, and we can check those very easily two different ways, either with a voltmeter and we trace voltage, or we could de-energize that circuit and put our ohm meter on there, determine if those are good or bad. But I have mentioned this before about the infrared testing, and if you're not using that currently for your predictive maintenance, then this is a great tool. I mean, this is something that gives us a true picture of exactly where our problem is and the extent of that problem. So infrared testing, you can see that immediately the picture to the right, I've got an issue, and I've got an issue on the left-hand part of this where it is coupled up to something, and it's probably a bearing issue. So when you can take a picture like that, it's going to give you so much information, and it's just really nice. So I just want to say this, that we do want to take a look at safety, because we want to be safe when we're doing all of this. So want to make sure we understand about OSHA 1910, which is general industry. If we're in the construction trade, it would be in 1926. Whatever our company says about safety, but the standard for electrical safety here in the U.S., of course, is NFPA 70E. So if we're tracing voltage, we should know what the incident energy is, we should know what the voltage level is, and protect ourselves from those two hazards. No doubt about it. This is some of the personal protective equipment that we do wear today. And a lot of this is for the amount of heat that might come from an arc flash or the bright white light. So I've got the face shield on. I've got arc-rated clothing on that will not burn. We've got the right meter in our hand, 1,000-volt rated tools. We got rubber gloves on with leather protectors to protect us from shock. So whenever we do any troubleshooting whatsoever, we want to make sure that we are safe, keeping ourselves safe and everybody around us safe also. So that's a little bit, but I want you to know that in this 1 hour time frame we have right here, I probably just can't tell you everything there is to know about what we would do in case a motor was damaged or not working properly. But And the other thing that we really didn't cover much of is the control circuit for that motor, how we would make sure that we're going to get power to that motor. But we have so many offerings for you. We have some online training. We have instructor-led training that goes much deeper. Our regular motor presentation is a full 2 days, and we actually put meggers in students' hands, and they meg out motors. We put meters in their hands, and they test the windings. And if the training is at your facility, I strongly suggest that the personnel there bring some motors in, and we check your motors out. So knowing that, I'm going to turn this back over to Ryan Smith, and he's going to wrap it up a little bit, and then he and I will answer any questions that came in. So thank you so much.
Thank you so much, Bob. And here you guys go. If you're interested in just learning more, or even if you just have questions about some of the technical content you just saw today, feel free to email this email address, sales@tpctraining.com. They're kind of our central hub for any inquiries, and you can feel free to get to us on, which of these classes are available, which locations they're available at, or for free quotes and things like that. Or call this number here as well. So with that being said, we got some really good technical questions to follow up on based on how motors work and operate. The first being, Bob, this first question that came in for us is, what are some of the main causes of insulation failure? So we know that's a big cause of motor failures in general. When the insulation breaks down, what might cause the breakdown of that insulation?
So it's definitely going to be heat. So heat is our enemy. So now we've got to determine where that heat is coming from. Is it the ambient? So is it our surrounding temperature that we installed that motor in? It wasn't very long ago that I had one of my students email me and say that he had taken an infrared picture of a motor, and it was about 10 degrees above the ambient. And my first question to him was, where did you install the motor? Well, it was in an attic, so it was extremely hot. And I told him, I said, 10 degrees above that ambient is normal, I told him. But we could have a problem sometimes with the ambient, but usually that heat is going to come because we have made that motor work harder somehow. So either we have overloaded the motor or we have a bad bearing, and that would create too much heat, too much current flowing through the stationary windings, and over time the insulation would wear down, and boom, we have a ground fault.
Gotcha. Thank you very much. We're getting a good amount of questions coming out. Let's see. For the megging of a motor, is it ever a good idea to use the megometer phase to phase?
No. So if we go phase to phase, what would happen is that current would actually flow straight through the windings, and there's not enough opposition there. There's not enough resistance for the voltage that we're applying, because normally we're going to be applying near 1,000 volts with that megger. So we really need the circuit from the copper conductor to the frame of the motor, because now that megger is going to build up a lot of electrons on that insulation, and it does it with capacitors. We build the voltage way up, and we put the electrons on the insulation, and we keep putting more and more and more electrons on that insulation until we can hopefully get through that insulation. And if we do, it would give us a specific number. And if we can't get through them, of course, we've got great insulation, so that'd be a great thing. But if we tried to do that between phase A and B, it's going to be a short circuit again, and it's going to short out our megger. So not a good thing. We have to have a very high opposition to go through so we don't damage the megger.
Got you. And now we only have 5 minutes left, you all, and we're definitely getting some really great questions to come in. So I'm going to try to summarize them the best I can. The first one being, The idea of using capacitors in your facility to correct power factor for motors, what is the best way to optimize power factor for using capacitors to maybe, let's say, even get up into the 90s for power factor?
Okay, so this is, and I'm going to give you an idea based on what I've seen over the years in facilities. And so I would caution you to not put those capacitors inside your facility. If you put those inside your facility, they are going to create some power quality issues at times, and they can play tricks with us. It's much better if you contact the utility and you say, listen, I would love to have some power correction capacitors installed on the exterior of my facility before it ever gets into my facility. I can correct the power factor on the load side of that transformer. And then the cost is going to come way down because the utility is going to be involved with us. They are motivated to have our power factor be close to 1 because they don't want us to be wasting their electricity either. And we're motivated because we don't want to have to pay a penalty. And the most cost-effective way to do that is to work with the utility and have them actually install the capacitors for us. They can monitor that power factor, get it very close back to 1, and that way, you're gonna. And there is a formula for it. The formula is kind of lengthy, but there's also a chart for it. That if I knew my power factor right now, I could come down and let's say my power factor was 0.7, and then I go to the right, it would tell me the size of the capacitors I would need to bring that right back close to 1. But I do want to caution people about putting them inside their facility. Let's try to work with the utility on that.
Got you. And let's try to do a couple rapid fire questions and answers here, Bob, for a couple of the loose end questions. One, is there a minimum speed requirement when you hook up a motor to a VFD? And does each motor have to have a different requirement?
Okay, that's a great question. So when I put a motor on a drive, sometimes the manufacturer will give us the parameters of the speed. I have seen that, especially with motors that are made to go on drives, inverter-rated motors, that the manufacturer will say, do not go over this particular speed. But as far as a minimum speed goes, I haven't seen the manufacturer give me too much on a minimum speed, but we've got to be very cautious because if that motor is not an inverter-rated motor and made for a drive, and I turn it really slow, then the fan turns really slow, and I have seen some motors start to smoke within 30 seconds of connecting to a drive because one, the motor wasn't inverter rated, and two, I was turning it way too slow. So we've got to be very careful about that. I can say that I like to maybe go in stages a little bit. I definitely would try 30 hertz and go at half speed, put an amp clamp on it, make sure I'm within the parameters of my FLA, maybe have something to sense temperature. And if everything looks good, then maybe go half of that, 15 hertz. But be careful if it's not an inverter rated motor.
Excellent. Thanks so much. And I'd say one more question I'll be able to get to. And again, you guys can ask additional questions and follow-ups with the email and the phone call. And that is, let's see. Let's talk about greasing, proper greasing amount. How do we know how often we need to grease? And then how much does proper bearing maintenance play into this greasing?
That's a great question. So immediately we have to know this. There is a lot of different kinds of grease out there, and you just can't choose something off the shelf without doing a little bit of research first. So we have to come back to the manufacturer of that motor. One, determine if the bearings are even capable of accepting grease. So if they're sealed, we're not going to grease any at all. If they're not sealed, the manufacturer will give us an idea of how often we have to grease that motor. Basically, we might be looking semi-annually, so every 6 months. And then you want to make sure you know how much grease to put in. And what I like to do is I like to take the drain plug out and I will put the grease in until I see a little bit of new grease coming out of that drain plug. I don't put the plug back in yet. I'll start the motor, get it real warm, and maybe let it run for 4 or 5 minutes, and then I'll put that drain plug back in. But the manufacturer is going to give us the guidelines on how much grease, what type of grease, and how often we grease it. We definitely have to look at the manufacturer's instructions.
Thank you so much, Bob, for your expertise on this topic. And that's going to conclude our webinar for today. Now, just to make sure everyone is clear that we will be sending out a PDF of these webinar slides for you within the next 2 business days, as well as audio and video recording of this webinar on our website. And we'll be sending you the link to that once we get it uploaded there. So expect that by the end of today or on Monday next week, and you should all be able to see that as attendees of this webinar. So thank you all very much for being here, and thank you all for your time. Have a wonderful, wonderful day.